The first counting problem we're going to look at is a puzzle called the Tower of Hanoi. So this puzzle was invented by Edward Lucas and involves a puzzle with 3 pigs, pig 1, pig 2, pig 3, and in a collection of discs. And the goal is to follow certain rules, so using allowable moves, end up with these discs in this order, but move to the second pig. So from largest to smallest, largest on the bottom, smallest on the top, we want to find a way to move these discs to this pig following the following rules. So we are allowed to move discs one at a time to any pig. So from one pig to another, we can move them from pig 1 to pig 2 or pig 1 to pig 3 and back and forth, as long as a larger disc is never placed on a smaller one. So our first move may be to move this smallest disc to, say, pig 3, because we want it to be on the top when we get to pig 2. So if we move this smallest disc to pig 3, then our next disc is larger, so that means we cannot move it to pig 3 because it would go on top of a smaller disc, so that means we'd have to move this larger disc to pig 2. But then coming to the third disc, it's larger than both the top 2 discs, which are on pig 2 and pig 3, so we can't actually move disc 3 to either of these pigs. So that would mean we'd have to move the smallest disc over here back on top of this larger disc, so that would be an allowable move, and then that would give us freedom to move this third disc to pig 3. And then we would want to repeat this process until we were able to move the bottom disc to pig 2 and try and build this tower back up onto pig 2. So that's the idea of the Tower of Hanoi puzzle. And our goal is to determine the smallest number of moves of the discs to the pigs that will solve this puzzle to get this series of discs exactly like this, but on pig 2. Okay, so we can use a recurrence relation to model the solution to this puzzle, so to count for the total number of moves to solve the puzzle according to the number of discs that we have. And so we'll be able to generalize the solution by building up a recurrence relation. Okay, so how do we do this? So we're going to let the sequence h sub n denote the number of moves needed to solve the Tower of Hanoi puzzle with n discs. And then we're going to set up a recurrence relation for this sequence h sub n, and then use our methods that we developed in section 2.4 to solve this recurrence relation, and hence give us the total number of moves. So each hn will stand for the total number of moves needed to solve the Tower of Hanoi puzzle, and we'll get a sequence. So depending on the number of discs, we have a value for every n. Okay, so we know that we begin with n discs on peg 1. And so we need to determine how to use a recurrence relation to model the solution. So we need to figure out how to go from n-1 discs, a solution with n-1 discs, to a solution with n discs. This would set up a recurrence relation. Remember that we want to write hn as an equation involving previous solutions of the puzzle with less discs. So if we can solve it for a fewer number of discs, how can we solve it adding one more disc? Okay, so we use the fact that we can transfer the top n-1 discs following the rules to the puzzle to pig 3 using hn-1 moves. So recall that h sub n-1 denotes the number of moves to move n-1 discs, technically from pig 1 to pig 2. But notice that there isn't really any special relationship, so the number of moves doesn't change, whether we want to move from pig 1 to pig 2, pig 1 to pig 3, or even from pig 3 to pig 2, or pig 3 to pig 1. So no matter where we want to stack them, it's independent. Our choice is independent of the peg. So this number, which counts the number of moves, will apply however we want to stack these discs in this particular order, moving them from one peg to another. So we know that we originally start with all of these discs, including this one, on peg 1. So our first solution to the problem, so our first set of moves that we're going to do is move these n-1 discs to peg 3. Because, remember, that we want to get the largest disc onto peg 2. It needs to be on the bottom, and then we want to move all of these back to peg 2. So we can use our recurrence relation, sort of like knowing that we know how many moves it takes for a previous number of discs, so n-1 discs, we can use that solution to solve for our n discs. So this is very similar to a proof by induction, or solving a recurrence relation, or giving a recursive definition. So you should notice some similarities between what we have done previously in the course. Okay, so this is the situation we're in. So we're trying to determine h sub n. So we're trying to write a recurrence relation for h sub n. So that means we know we're going to need to write that in terms of previous members of the sequence, and in particular, we actually only need to consider the previous term, so hn-1, because here's our strategy. So we want to get the bottom peg onto peg 2. So that means we need to move the top n-1 discs off of this bottom disc, so off of peg 1, so that we can move this disc to peg 2. So we know by our definition of this sequence that we can move n-1 discs from one peg to another in this order using h sub n-1 moves. So we first move these n-1 discs from peg 1 to peg 3, and since it doesn't matter which peg we move them to, that doesn't affect the total number of moves that we need, we know that transferring these discs from peg 1 to peg 3 can be done in h sub n-1 many moves. Okay, so now our next move is to use one move to transfer this largest disc from peg 1 to peg 2, and then we want to move these n-1 many discs on top of that disc onto peg 2. So again, transferring n-1 many discs from one peg to another, we know takes h sub n-1 many additional moves, because that's how we defined our sequence. So our recurrence relation then is to move n many discs from peg 1 to peg 2 takes hn-1 many moves to move those n-1 many discs to peg 3, and then one move to move that biggest disc to peg 2, and then another h sub n-1 many moves to move these n-1 many discs back to peg 2. So that was 2 times h sub n-1 many moves plus that additional move to move this disc to peg 2. So this gives us our recurrence relation to model the total number of moves to solve the Tower of Hanoi puzzle with n discs. The other thing we need to consider, recall we're developing a recurrence relation, so we need to set up our initial conditions. Notice that we only have a recurrence relation involving the previous member of the sequence, and so we need only one initial condition set up. So we just need to determine how to solve the puzzle for one disc, and there's simply one move to transfer one disc from peg 1 to peg 2, and so h sub 1 is equal to 1. And as soon as we have h1, then we can calculate the values for each of the h sub n's by simply subbing those values in to this equation. So h2 would be 2 times h1 plus 1, which is 5. 2 times 2, which is 3. 2 times 1 is 2, plus 1 is 3. So h2 would be 3, and we could build up our values for our sequence in that way. But recall we actually want to solve this in general, so that means we want to find a closed formula for h sub n involving the index n, and so we do this using the iteration method that we talked about before.